It's going to give us more kind of exposure to molecular orbitals. Probably help on the final. But it's in some sense, I'm going to test you directly on this material. I just want to illustrate an interesting story about a rather boring molecule, methane. One more thing I want to say is that I say this every year. The student evals are up. Please, you guys, have a moment. Either a positive or a negative comment. I like both. They really mean a lot to me, and I've changed my class over the years because of those comments. Every year is a little different because of that. Obviously, there are some intricacies and quirks that I have that are hard for me to kill. I do my best, make it as accessible as possible. So I want to teach you a lesson about how not to think about things that you think are identical aren't really identical. And methane's a really good example of this idea of what identical means in chemistry. And this actually is a very, very deep conversation. We spent a whole semester thinking about this idea of things being identical or indistinguishable in chemistry. And what happens is that when you have indistinguishable things that you put into a specific orientation, and in the case of methane in a tetrahedron, we find that even though all of the hydrogens are exactly the same, we're going to learn that not all of the electrons are created equal. Right? So it turns out that something being chemically looking equivalent doesn't mean at the electronic level, microscopic level, that everything is equivalent. And that is a really, really interesting example. So what I want to think about is let's just think about methane from an organic chemistry perspective, just about the bonding. And then let's just try to think about what the molecular orbitals of methane may look like. And there's this idea again that methane is constructed by hybridizing S and 3Ps to form 4 equivalent sp3 molecular orbitals. Right? And when we do that, we learn that when you hybridize carbon, the sp3, and you just stick hydrogens on that carbon, the simplest result of that, of course, is CH4, which is methane, right? Which is where you get a tetrahedral geometry where all the hydrogens are equivalent. Every hydrogen is exactly the same, and they're all split by, right? We get this nice 109.5 degree bond angle, and all the bonds are the same length, right? So we obviously say that each CH bond in some sense is equivalent, right? Each CH is equivalent. So there are 4 equivalent. I have a feeling it's going to crash on me. Oh, it is. Yeah. It's so hot in here. I knew it was going to be a bad day today. So we would say that this has 4 equivalent CH bonds. Right? So we would think that maybe the molecular orbitals that are formed that create these bonds are equivalent. There are 4 equivalent molecular orbitals, each with 2 electrons, one from the hydrogen and one from the carbon. Right? So maybe we can think, let's just kind of naively do this, right? We know that carbon is 1s2, 2s2, 2p2. Right? So I'm going to define these to be in a specific orientation. So we have our 2s box. We're going to put one of the p electrons in the x and one of the p electrons in the y. Right? So let's say carbon has that arrangement. I could put the p electrons in any orbitals I want, but I'm just going to for convenience put them in x and y. There's no reason not to put them in other ones, but just to set this. And so we've got our 4 electrons. We also have sorry, I should put the empty Z orbital. Sorry, I forgot the other one. Right, we have 2pz, which is empty. Right, and we know what these look like, right? These are sphere. This is a sphere with a funny shaped color core in the center. And we can draw px to be vertical, pz to be horizontal. Actually, no, let's not do that. Let's py to be horizontal. And then z out of the plane, like that. Okay? I'm just making a choice. Right, and then we would say, okay, well, what I'm going to do is I'm going to add sp, x, and y, and z in a combination. So I'm going to put in 3 atomic orbitals, and out of it, I'm going to get 4 combined hybridized orbitals. So I'm going to mix them in a specific way, right? I'm going to, let me see where I can put this here. I'm going to add them together in such a way where I take 25% of the 2s and 75% of 2p. Right? I'm going to mix them together in that ratio. Going to give me a combination that looks like sp3, where everything is kind of equally weighted. Right? And so I would expect naively that the resultant molecular orbitals, right, I would get these sp3 orbitals out that are all equivalent. Right? And each one, right, I have, the carbon brings in 4 electrons, and each hydrogen brings in 4 electrons. So now I've got to add the hydrogen. And we're going to bond these to 4 equivalent 1s1 hydrogen atomic orbitals. That gives us 8 electrons. So we get 4 from the carbon. And then we get each of the hydrogens bring in 1. Right? So we would expect, right, we have 4 bonding orbitals, right, that are all fully filled. And they're all equivalent. Okay, so great. So our idea is that just from thinking about just very simply just adding hydrogens and carbons together and taking advantage of the, what would you say, equivalence of the hydrogens and methane, right? The symmetries of methane, that we should get 4 equivalent bonding orbitals, each corresponding to one of the CH bonds. Great. Now the question is, of course, what happens when I remove and I ionize methane and I remove an electron? So now what I'm going to do is ionize this. Right, in my photoelectron spectrometer. And I'm going to remove an electron from one of my bonding orbitals, right, which are the highest, those are the valence orbitals. So they're the highest ones, are the ones with electrons leaving first. The question is, where does the electron come from? Well, they can come from 4 different places. They're all equivalent. So our claim is that there's only one valence excitation, meaning that you remove 1 electron from any one of the 4 orbitals, they're all equivalent. So we would expect that this would lead to 1 ionization energy corresponding to removing 1 electron from any of the 4. All right. So in our little ionization spectrum, where we see the resultant ion, we would only expect to see 1 peak in our valence band, because the electron can come from any one of these 4 equivalent orbitals. So we'd expect to just see 1 peak in our absorption spectrum. That seems like a really reasonable way to construct methane. We'll have to come back to the tetrahedral part of it. We haven't considered the tetrahedral part of it at all, but maybe that's just neither here nor there. That's just an artifact of the electronic structure that happens to be the best way to arrange these, which is true. But we're going to find that, in fact, the fact that we have to arrange these orbitals in this tetrahedral geometry ruins this hypothesis. Let me prove to you why this is wrong. But what we're going to see is that this is not correct. All right. I have one picture to show you that shows that this is not correct. The proof of that is the photoelectron spectrum of methane. Right? We just go take the damn spectrum. And I just pulled this from Google Images. There's lots of different studies of this. Methane is one of the best studied molecules. So this is the photoionization spectrum. This is the ionization energy down here. That's a kind of blurry, I apologize. But this is, you could also say that this is binding energy. And this is in kilojoules per mole, which is kind of a strange unit. We usually use EVs, but 1 kilojoule is roughly 96. Oh, sorry, I got that wrong. 96 kilojoules per mole is about 1 EV. All right, so if I divide all these by 100, I get roughly the EV, right? So in EV, this is 22, 20, 18, 16, 14, and 12 EV. So remember in hydrogen, remember in H2, for instance, the binding energy of H2's electrons around 16 EV. The valence in nitrogen is around 18 to 14. So these are valence electrons for 2p. Right? This is right around the same area that the valence electrons for nitrogen. Right? So this is the N equals 2 valence. And notice that in the valence, this is methane, right? So we're in the valence, we're removing valence electrons. Those valence electrons are in these bonding orbitals. These are bonding electrons. And notice that there are 2 p's. There are 2. So what this means is that there is an electron at around 21 minus 21 EV. And then there's another set of electrons at around 13 EV. Notice that there's an intensity difference too. These are proportional to the fluxes of those electrons. And the ratio of the intensities is 3 to 1. So there are 3 electrons in it. Or rather, there's 6 of them, but they're all equivalent. There's 3 different orbitals here. And there's 1 orbital here. So there's 6 electrons in this orbital, and there's only 2 electrons. So we've constructed methane incorrectly because this shows us there are 2 distinct sets of orbitals, not 1. Doesn't that disprove our equivalence principle? Well, of course it doesn't, because this is an experimental result. I know that this is correct. I know that methane is 109.5 degrees tetrahedral. We can prove that. It was proven for over a century. Let's say 2 centuries that we've known that about carbon. So it's not like this is disagreeing with any sort of known reality. This is the reality that these equivalent hydrogen CH bonds, 4 equivalent CH bonds, split into a combo of 3 and a singlet of 1. Let's try to understand why that is. How can we reconcile these 2 things? We have, in some sense, an asymmetry here and a symmetry over here. Turns out that's the wrong way to look at this. That in fact, this photoelectron spectrum is a product, is a result of this symmetry, of the fact that these are equivalent. And in particular, the key thing is that this is due to the fact that it's tetrahedral. So what we generally find is that tetrahedral systems in chemistry, whether they be orbitals or different types of things that are tetrahedral, always split. Sorry, this is supposed to be always split into a 3-to-1 combination of two states. This is a product. This is the end result of the fact that we have a tetrahedral molecule that everything is equivalent. This is the fact. This is because it's equivalent. The electrons are distinguishable between the two states. That seems counterintuitive, but I can show you with just some pictures that we can justify by taking advantage of our construction, our tetrahedral geometry. I can show you that this splits into a 1 and a 3 set of orbitals, a triplet and a singlet. So let's look at that. So the problem with our, again, I'm just going to repeat myself one more time. The problem with our original construction is we didn't take advantage of the geometry. We didn't look at a tetrahedron. And that's the important distinction that we fixed it with the geometry. We have to take advantage of the fact that it sits in the tetrahedron. So let me show you a cool way to construct the orbitals of methane, taking advantage of its tetrahedral geometry. Right. So what we're going to do instead is we're going to, instead of construct, and what we did originally is we took the carbon orbitals and we combined them all together, and then we added the hydrogens to it. Right? I hybridized the carbon on its own, and then I just added hydrogen. So now it turns out to be the problem. What I should start with is a system that has both carbon and hydrogen in it together, and then hybridize the whole set. So the hybridization set includes the 1s orbitals of hydrogen as well as the carbon valence, instead of doing the carbon valence by itself and adding the hydrogens. That requires us to put the hydrogens in the right place relative to the carbon. So we have to construct our orbitals not on a line, but in a tetrahedron. And a tetrahedron is just basically a structure embedded in a cube. So let's draw some cubes. So we're going to hybridize our carbon 2s plus 2p plus 4 hydrogen 1s1 orbitals. We're going to put it all together in a single construction and place them in a tetrahedron. So this requires a tetrahedral geometry. So let's build our first cube. Right, I'm going to add 4 carbon orbitals together, 4 hydrogen orbitals together. I need to build 4 cubes. I'm sorry that you guys have to, it might be useful just to copy one, and then you'll see that you can draw it without the cube later on. But so let me construct 4 cubes. I'm going to put the third one here and then the fourth one here. So I've got 4 cubes here that I'm going to place my orbitals in a tetrahedral array. The way I'm going to do that is I'm going to embed the carbon in the center. Actually, so I'm going to put the carbon in the center. And then I'm going to put the carbon goes in the center, and then the hydrogens go at different vertices, different corners of the cube. So one of the hydrogens, 1s orbitals, will be right here. The other one will be right here. Right? So that, remember, 2 are on our plane and the other ones are out of plane. So it's going to be in the front left corner and the back right corner. So these are our hydrogens. How do I know generally what the wave function should look like for the ground state? We know that in general, the ground state of any wave function needs to be even. Remember that the v = 0 state is always an even function. Right? The ground state of the particle in the box is an even function. There's no nodes, it's just like a half period. So everything should have the same sign in the ground state. Right? So the first thing I'm going to construct is to think about what this state looks like where all the hydrogens are of the same phase. Right? We're going to add them all together constructed. No nodes. So I'm going to add a plus hydrogen up here. I'm going to add a plus hydrogen here. And a plus hydrogen here. And a plus hydrogen here. Okay. And so the question is what orbital in carbon should I embed in the center that maximizes the overlap with the hydrogens, right? What's the best fitting orbital? And the fact of the matter is that above and below the plane of the carbon, we don't change any sign, right? The whole thing is even. So I better put a function that looks spherically symmetrical in the carbon, right? So that above the plane, the top half of the cube is all positive, and the bottom half of the cube is all positive. I do not want to put a p orbital in there because that changes signs. It's going to cancel out. It's going to create a node. So the only thing I can put in here is the 2s orbital. Right, so the maximal overlap will come from taking carbon 2s. Right? And you can see I get basically 4 bonding combinations between all of these orbitals. And I get a positive combination here, get a positive combination here, and a bonding combination here. Right? So this is carbon 2s plus 4H1s, and this has 0 nodes. Right? So this is the ground state. This is the lowest order combination of taking 4 equivalent hydrogens and adding one of my carbon orbitals. It's the best combination I can make. But now I've used my 2s orbital. So for the other ones I have to construct, I have to use the p's. P's are odd, right? So that means I'm going to have some nodes in my function, right? I'm going to have some sign change because I'm going to construct p's. So let's embed our p orbitals here. Let's define our coordinate system to be z up, x to the horizontal, and y out of the plane. So I'm going to, in these orbitals, I'm going to put my e's in the center. So we have the pz. We have the px. And the py. Oh, that's not a very good p. Okay, I got to give them signs, right? Because they change signs. So we'll just take this away like this. And the question, of course, is now I have to take 4 hydrogen orbitals, equivalent orbitals, and put them in a way that's constructive, as maximally constructive as possible, right? So I don't want any negatives and positives, much like that. Right? But there's going to be a node that forms because the p orbital itself has a node. There's 2 sides, right? In some sense, I've subdivided the cube into a positive region and a negative region. I can draw little planes of symmetry. That subdivide this system into a positive region and a negative region. It's that plane here. And then the other one kind of goes through the center. That one's a little hard to draw. Right? You can see that this subdivides, right? I now have a cube that now has 2 faces, as positive and a negative face, right? So this allows me now I have to be careful about the way that I add the hydrogen. I want to maximize the overlap. And so, of course, here, right, I'm going to add negative. I'm going to add negative ones here and positive ones up here. So right, so one of my choices is going to take two positives. And then I get two negatives on the other end. Right, so these interact constructively with the negative load. And these construct positively that load. Right? And this has a nodal plane, right? This is effectively a plane through the molecule where the electrons can't exist, right? For achieving signs. And then exist across that entire red plane. So we can say that this has one node. It has a node plane, the nodal plane. That subdivides the molecule, right? So I've gone from a wave function of 0 nodes to one that has one node. They're different wave functions and therefore have different energies. And we generally know that the more nodes you have, the higher the energy. It's the way we've always analyzed this. So this is a different orbital. It has different properties. It has a node. It will definitely be what am I going to say? A different energy orbital. How do we construct the other ones? Well, that's pretty easy. We just do the same thing. We have a negative here, negative here, positive here, and a positive here. Right? And if you notice, this is exactly the same thing. I've just rotated it. This is exactly the same orbital construction as this one. I've just flipped everything on its side. So this has one node, nodal plane. Right? It's the equivalent orbital, just rotated. Now let's look at the final one. This one I'm going to put positive here. Oh, sorry. So the negative side is pointing out of the board. I have this is pointing this way out. Blue is pointing out. So I want the negative or hydrogens on the front face. Oh, sorry, that's not where they are. Here. And then I have the positive hydrogens on the opposite face. I think I've actually screwed my line up. I'm sorry, guys. Let me fix that really quickly. So let me draw my hydrogens one more time. So I have a positive hydrogen here and a positive hydrogen here. And the nodal plane is going to cut through the two that don't have hydrogens in it. It's really tricky to draw here. What have I done wrong? Oh, okay. Yeah, I see where this is being cut through. It's cutting through the middle of the box. Let me draw it in red. So the nodal plane is through the middle of the box. I think it's going to crash one more time. Yep. But I just saved it. I think I'm good. Oh yeah, fantastic. Okay. So let me fix this up really quickly. So let's always add the hydrogen. I should add the hydrogens first. So we're going to have the negatives on the front plane and the positives on the back plane. Right. And the symmetry plane is through the middle of the box. It's going to crash again. It doesn't like when I draw like that. Whew. I know one thing I'm going to do is I'm buying a new laptop this summer. We've had this one since 2017, so I've done pretty good. So let me I'm not even going to draw the nodal plane. I'm just going to do this one more time just so we have it. And then we don't have to worry about it again. Right. It's pretty easy to see that this is exactly the same orbital. I've just rotated everything, right? It's the same thing. So this has one nodal plane, right? And so what I've done by embedding, right, by thinking about the hydrogens as being equivalent, and then adding the equivalent hydrogens in the right geometry to the carbon atomic orbitals gives me two sets of orbitals. Gives me a fully even combination and three odd combinations. Right, so we have three odd combinations and one even. All right. So the whole point is that the symmetry, the geometry, symmetric geometry of methane is what imposes the different orbitals in methane. It comes from the fact that because you embed, you can only the best way to construct for equivalent hybridized orbitals is to have them separate into two groups. So now let's think about what the molecular orbital diagram looks like for this. So I've got it. We're going to build a diagram. We're going to start with carbon on the left and 4 hydrogens on the right. Right? We should look up where the carbon orbitals are in energy. So here's the carbon ionization energy. The first one, which comes from the P's, is at 11. And the second one is at 24. So we have our p orbitals at around 11. They're at 11.7 to be precise. We have 3 equivalent p orbitals that are just 2/3, well, 1/6 filled. And then at around minus 22, we have the carbon 2s2. Okay. This. Right, and what about the hydrogen orbitals? Well, the hydrogen orbitals we put in a tetrahedral arrangement. We're adding them all together, and we saw that this forms a singlet and a pair of 3. And the pair of 3 should be higher energy because they have a node. And so at minus 13.6, right, because that's where the hydrogen ionizes, we're going to have a small splitting. I don't know what it is, but we're going to have one state, and then we're going to have a triplet, right, where everything is filled equal amounts. Right, this is our group. Okay. And the combinations of these, right? We saw that the 2s combines with the s orbital, one of them, and then the other one combines the other set. Right, so we're going to get a bonding combination from this orbital. That's the even combination. We get an anti-bonding orbital. So that's our first combination. And then we get the p orbitals combined with this triplet set. So we're going to get a triplet set of molecular orbitals. Slightly higher energy. Bless you. And a set of anti-bonding orbitals that are also triply degenerate. Right? We saw that these are roughly minus 15, and this one's at minus 23. That's what we saw in our the spectrum that I showed you at the beginning of the class. And we can fill these up. And we have 1, 2, 3, 4, 5, 6. Okay. And so what we have now are 4 bonding orbitals. Right, we have 4 bonding orbitals, but it's not a quadruple bond because it's split over four different bonds, plus 4 bonding atoms. So this equals, of course, single bond per CH. Okay. And so the geometry, the tetrahedral geometry itself is what imposes this structure, right? This difference. So it's the fact that we have different bonding orbitals, different molecular orbital constructions, is a consequence of the indistinguishability of those 4 hydrogens, not a contradiction. It was a product. And these kinds of motifs, the idea that when tetrahedral things form, they form a combo of 1 and 3. We saw last class with ammonia that the combination of 3 equivalent things gives you a combination of 1 and 2. These are things that just appear all the time in chemistry. These are products of molecular symmetry. And so these are repeated motifs which is like 3 plus 1 for tetrahedral, and 2 plus 1 for trigonal, pyramidal, are due entirely to molecular symmetry. So the symmetry of the molecule determines the bonding characteristics. And the fact of the matter is that all tetrahedral objects have this. This comes from the symmetry of the tetrahedral. There's the entire field in chemistry where we study symmetry. In fact, in spectroscopy, we just finished a whole module on studying exactly this kinds of symmetry properties. They teach you something about vibrational spectrum. You can learn about how vibrational modes, for instance, because if you have molecules of specific symmetry, the vibrations also have to satisfy those symmetries. And that leads to specific vibrations. And so you can predict exactly what vibrations will happen in a molecule if it has some sort of symmetry. And so there's a process of identifying the symmetry, constructing a system, and then symmetrizing it. And you always end up getting these kinds of repeated motifs, things like 1 plus 3s and 1 plus 2s, things like that. So they're completely consistent across chemistry. In fact, they're mathematical requirements. They're mathematically rigid. And so people study them very deeply because you can learn a lot about how a molecular geometry changes if you are able to track the orbitals. Imagine here's a really interesting, I want to show you kind of a final discussion of this, an application of this idea. I want to think now about what happens to methane when I pluck a hydrogen off. We notice what happened with an electron. Two different types of electrons exist. Now, what happens to the molecule when you pluck a hydrogen off of it? Right? So if you go from methane and you put a bunch of energy into it, you use a laser, and you pluck a hydrogen off, where you create a free radical. The question you may wonder is, what's the geometry of that methyl radical? Does it change? This is initially tetrahedral. But the question, of course, is what is this? Does it continue to be tetrahedral? Well, there's some options. Because of Vesper theory, VSEPR theory tells us that if you don't have a lone pair on the other part of that carbon, we might not get a trigonal pyramidal geometry or trigonal pyramidal where everything will bend into a tetrahedron. Having that one extra electron makes things tricky. People have studied the methyl radical for a long time. And when you look at the photoelectron spectrum of this, right, where you take CH3 radical and ionize it to CH3 plus H. Interestingly, what you find in the electron spectrum is a peak here around -18, and then another peak around -12. That's 2 to 1. So in tetrahedral, we see a 3 to 1. And then in methyl radical, we see a 2 to 1 distribution. Just write that over here. You don't have to draw it, but just so we have it. So 1 to 3. So what gives? Clearly, the geometry has changed because now my electrons are being plucked from 2 orbitals in this box instead of 3 orbitals. That means the geometry has changed, and it's changed to a 2 to 1. This is confirmation just from the same construction that we did for the tetrahedron. You can do the same kind of idea for something that gets 2 to 1. And what this shows is that CH3 is planar. It's trigonal planar. This has that same 2 to 1 symmetry that we saw for the hydrogens and ammonia. So this is tetrahedral and non-planar. And then when you remove a hydrogen, the carbon, it's like the hydrogen's kind of like they're not being repelled anymore, so they move into the plane. And that extra lone pair is sitting above the plane. Sitting above the plane, just kind of hanging out on the carbon in the p orbit by itself. All right, so this is really interesting. There's a symmetry change where the orbital construction has changed between the two. And so the orbitals have resymmetrized. Very interesting. Now, for a long time, people thought that this is effectively an instantaneous process. Okay, think about watching this and watching a video, watching the orbitals isomerize from having 3 equivalent in the valence to having 2 equivalent. How does that happen? And no one was ever able to take a photograph. And the reason why is because this process is extremely fast. I'll show you how fast it is in a second. Right? But someone finally, a couple of years ago, finally photographed this process. The 2 endpoints have been known for a long time. I mean, I've even studied methyl radical myself, and I don't even do that. So it's a planar molecule. It's really, really well known. And of course, methane is known to everybody. The endpoints are, but it's about the mechanism in between that's really interesting. The question is what you're doing is you're removing an electron and a hydrogen very, very quickly with a laser. How fast does this process happen? What's the reorganization rate of the carbon? Things have to move. So someone a couple of years ago finally took a video of this. I want to show you, so I want to talk a little bit about this experiment. I'm going to show you this really interesting picture. Right. This is showing us, and we'll see in a second. Oh, this is a different, this is not the, this is a slightly different Sorry, this is wrong. I thought this was removing hydrogen. I have the wrong paper up, but that's okay. We can look at this one anyway. This is the same process as CH4 to C. We're looking at the ionization of methane here. I apologize. The interesting thing is that this does change. Okay, so in CH4 we have orbitals that look like this. Right, this is our valence for CH4. Right, and in CH4 plus, the orbitals actually arrange slightly differently. Oh, sorry, I need to add. Oh, that's right. There's 5 of them. 4 of them. They rearranged the 4 of all different energies. 1, 2, 3, 4, 5. Okay, so this process goes from this arrangement to this arrangement. All right, so what happens in methane is actually in ionized methane, the CH4s the H's isomerize and they become non-identical. And I can show you a picture of this, of what this molecule looks like. Right, so this is the structure of CH4. Remember the Born-Oppenheimer approximation. Remember the nuclei are very slow. So when we remove the electron from methane originally, we kick the electron off. The molecule hasn't moved yet. All that was called a vertical excitation, meaning that the electron gets plucked off before the elephant ever gets a chance to relax. So initially, the methane cation still looks like methane. Okay, but when you remove one of those electrons from the p orbitals, that set of triplets from CH4, the triplet from CH4, the whole system isomerizes into this organization that is of slightly lower energy. It's what's called Jahn-Teller distortion, which is where these orbitals rearrange basically to take that unpaired electron and move it away as far as possible. Because the electron I'm removing is this one. Right, we're unpairing the electron next to it. So we want to take that electron and move it away from the other electrons. And so now there's a hole here and it's far away. Right, so it's the molecule has moved the electrons around to minimize the repulsion of that unpaired electron. And you can see it messes the structure up a little bit. Now you have 2 different sets of hydrogens, one that's 125 and one that's 55. So we've broken the symmetry. Right, so this process you can see with photoelectron spectroscopy, something that has been well studied. The question is how do you observe it? So something that instantaneously happens or not? Let's say here something about 10 femtoseconds. So this process takes on the order of 15 femtoseconds is 10 to the femtoseconds 10 minus 15 seconds, right? So that's 10 quadrillions of a second. Yeah, 10 quadrillions of a second. It does this process, right? You have to have a really, really fast camera. So here's the way that they did it. It's a little complicated, but I'll walk you through the process. Okay, so the first thing that they do is they use a very, very strong electric field to remove one of the electrons, the strong field ionization. Okay, so the first step of their process is they run methane through this strong field and it plucks an electron. You put in a molecule in a strong enough electric field, will just sleep. So that creates a hole, right? There's a gap now. And so once that ionizes, they do they do 2 light sources. They do two light. The first thing they do is they take an electron from the core. This is the 1s. This is the 1s2 orbital of carbon. And they excite it with an X-ray to put it in that hole. Right? So they're replacing the electron they lost with an inner electron. Right? And then what they're going to do is they're going to, oh, sorry, I apologize. I take that back. So what they're going to do is they first pump this with a laser and kick it off. So the pump is the first step. I apologize. So they use a really strong pump laser to ionize it. And then after some amount of time, they take this electron and they put it in here. Right? So at some delta T, they delay the process. So if delta T is 0, what we would expect is that you would remove this electron and then it would immediately substitute back up in there. And the energy of that X-ray, of that absorption, is going to be the difference between the 1s orbital and this tetrahedral orbital, the hole up here, for this CH4 geometry. So you would expect it to be, you would expect the absorption at what they say is 278 feet. Okay? So you would see an absorption at 278 at 0 time delay. Now, as you start to step the time delay between the pump and the probe, the geometry is going to isomerize over to this. Right? So the nuclei are moving at the same time. And so if I wait long enough and I do the same process, I'm going to see an absorption at a different energy, because now those tetrahedral orbitals have distorted, and now I have to cover more of a gap to fill that hole. So the absorption is going to be at 281. So I have two endpoints of my spectroscopy. If I catch it early enough, I'm going to see it at 278. And if I catch it late enough, it's going to be at 281. Question is, of course, how long does it take for it to transition? No one's ever seen that. And the cool thing is with X-rays, nowadays with X-rays, the way that we can make X-rays, these are tabletop X-ray lasers. Actually, I think this one was founded by Freeland. One of the powerful things about creating an X-ray laser, the way we construct X-ray, we build X-ray photons, we energize the light for X-rays. You have to compress the light. Basically, you stack photons and they get stronger and stronger and stronger. You can build them up more and more and more. The way that they do that, it causes the width of the light pulse to shorten. So as they start to make the photons more, the light laser pulse more and more energetic, laser pulse gets shorter and shorter and shorter and shorter. So by the time they promote it to X-rays, the pulse length is not femtoseconds, but hundreds of attoseconds. Right? It's like what's that? What's below a quadrillion? Quintillions, right? 100 quintillionths of a second. That's how long the X-ray is on. The X-ray oscillates only for a few periods. Extremely short pulse. And the 800 nanometer pulse is on the order of about 5 femtoseconds. So what that allows us to do is to basically step the probe at different time points, and effectively it's a different frame of this animation. Every time you step the probe, it's going to move it's going to be between some limit here and some limit here. You're going to see an absorption at different time delays. That's going to change. Right? It's not going to be a step where it's going to be at 278 and someone's at 281. The hypothesis is if we picture it fast enough, we'll see it smoothly move. Okay. So this was done at Berkeley. And here's the result. Beautiful picture. So this is a picture of the spectroscopic results as a function of the time delay. Sphere on the left and theory on the right. And you can see pre-time, the absorption is around 278, right? That's tetrahedral. 0 is where the X-ray photon ionizes the molecule. Right? So we have CH4 here. And then suddenly we have CH4 plus. And then every time step, the probe laser is, well, the pump laser is hitting at 0, and then the probe laser is kicking in and measuring the absorption of that electron at each point. You can see that it moves. Right? Over the course of about 10 femtoseconds, it moves from 278 to about 281.5. And then it flattens out after that. And that's exactly consistent with theory as well, that there's this smooth but very extremely rapid chain where you're watching, this is literally watching the elephants start to relax as we fly over. Right? It's a very, very fast process. But one time when I was a graduate student, someone asked me a question at a poster session about spectroscopy. And asked the question, when you excite something from one state to another, is that instantaneous? Because we're going to say excitation is an instantaneous process. And the answer is no. Very much no. And this is an example of a really great example of a process that is photo-driven. right? We're doing spectroscopy on a reactant and a product, and you can see that if you have fine enough time resolution, you can watch the system transition from one state to another, one spectroscopic transition to another. And if it's fast enough, you can watch it in between as well. Right? So every spectroscopic transition has a time scale at which it takes to go from the initial state to the final state. It's just absurdly fast for molecules. Right? So it's not until the last 10 years or so that we're able to take pictures like this. Since new technology for us to be able to take pictures on the order of just, a femtosecond. I've had some luxuries to do experiments like this before, but never quite with this sensitivity. Our time resolution in my femtosecond experiments was about 10 femtoseconds. So each of these steps was a step for me, but for them, they have about 5 or 6 steps every 10 femtoseconds. It's really, really impressive for them. So it's one of the hardest experiments to do, and you're literally visualizing one of the fastest processes of chemistry that have been. So very cool. All right. Do I have anything else that's cool? No, not really. I think that's about all I have to say. Thank you all. We'll get done early today. Please give me 3 emails. I'd really, really appreciate it. Homework is due sometime.